The sun is obviously yellow. I mean, look at this beautiful sunset or this picture from NASA. Only it's not yellow, and I can prove it to you right now. The sun is white.
But that's not quite right either, because if the light from the sun was pure white, then it would be an equal amount of all of these different colors. But it's actually mostly green. Why green? Figuring this out actually led to the quantum revolution, and I really want to tell you that story because it's very interesting. But first, let's figure out why isn't the sun yellow? This is NASA's official page for the sun, and you can see that it's full of images like this, of the sun looking like a yellow, red, fiery ball. And if you scroll through the rest of these images, you'll see mostly photos of the sun looking red and yellow, but occasionally you'll find one of the sun looking white. But there are also images like this on the website, where the sun is shown in many different colors. So what's going on and what is the actual color of the sun? Well, these images aren't false exactly, they're just false colored. So in this case, NASA took the same photo of the sun in many different parts of the electromagnetic spectrum. But because our eyes can't see most of these parts of the spectrum, NASA has to choose which way it's going to display it to us in our usual color range. And so they have a choice. They could choose any of these colors, but they just so happen to keep choosing yellow. You'll get a very different picture of the sun though if you look up images of the sun from space. In those images, you can quite clearly see that the sun is actually white. If anything, it has a bit of a blue-green tinge around it. If the sun is actually white with a bit of a blue-green tinge to it, then how come NASA keeps showing us images of the sun that are yellow? Is it NASA's fault, or is it really ours? So this website from Stanford University's Solar Center sums up the situation really well. It says, "It's hard for many people, even scientists, to admit that the sun that they're so used to living with is actually white. So sometimes they even color pictures of the sun taken in visible or white light to look more like something we would expect. Below is a picture of the sun taken in visible white light, but which scientists have processed to make it appear orange for our benefit." Why are we so insistent that this is how the sun looks? It's because of sunsets. Look at this beautiful video of a sunset I took during my last holiday. Sunsets are basically the only time that any of us actually look at the sun. I mean, there are sunrises as well if you're an overachiever, but either way, both of those really skew our picture of the sun, and that's because of the atmosphere. So imagine this is the Earth, this is you, and this is the sun, and this is a molecule inside of the Earth's atmosphere, and all of this is not to scale. You can see here that the sun is outputting all these different types of light, and so you should see the sun as white, but this molecule is what's going to change things. All of these different colors are coming from the sun, but when it hits the molecule, only some of them will continue through and hit you. Blue, and to some extent green as well, are more likely to be scattered away by this molecule, whereas yellow and orange and red are more likely to actually hit you. This phenomenon is called Rayleigh scattering, and it's what makes the sky blue, because when the blue gets scattered away, we think that the blue is coming from the atmosphere, not from the sun. But it's also the reason that the sun appears yellow to us. Because if you think about it from our perspective here, only really the yellow, orange, and red light is hitting us from the sun, whereas the blue-green light is getting siphoned off. And so from our perspective, the sun itself looks like it's red or yellow. But the important thing is that Rayleigh scattering is going to be way stronger during sunrises and during sunsets. Think about it. If the sun is just rising, then what's happening is you're seeing the sun through a whole lot of atmosphere. The more molecules between you and the sun, the more scattering there is. By the time that the light actually gets to your eyes here, only the red will have directly made it from the sun, whereas the blue and green get scattered into the rest of the atmosphere. and so that's why sunsets look so red. But if instead it's noon and the sun is directly overhead, then there's going to be way less atmosphere between you and the sun. That means a lot more of the blue light will have actually made it to you without getting scattered at noon. And so the truest color that you can see from the sun is if you squinted it during noon. The problem with that though is that because there's so little atmosphere between you and the sun at that point, there's a lot more light that's going to be hitting your eyes, and this is why it's dangerous to look at the sun during noon. So exactly at the time of day where we can get the best picture of the sun, it's dangerous to do so. But at the time of day where we're actually able to stare directly at the sun because of all of this atmosphere in the way, we actually get the most skewed picture of what it looks like.
I'm really excited about the sponsor for this video because it's a charity that I donate to, and I'd like to explain why. So here's a stat that might surprise you. Over 99% of farmed animals in the US are raised on factory farms, and the vast majority of people, 90%, say that they oppose the conditions on these farms. So almost all of us think that this situation is unacceptable. FarmKind is a charity that aims to be maximally effective at helping these charities. What they do is they research many welfare organizations and looks at their track record and their cost effectiveness, and then based on that, recommends some charities to donate to. So if you donate through FarmKind, say for example you donate $12, then they give all of that money to those recommended charities, and you can see your impact because they calculate in expectation how many animals your donations will help per year. I think it's amazing that so little money can completely transform the lives of this many animals per year. So if you want to donate as well, the link is in the description. Thanks.
I think there's also one other important bias going on here. We think of the sun as extremely hot, like a fire, and fire is orange and red. But the sun isn't yellow hot, it's white hot. It's way hotter than flames, and that's what makes it white. Let me explain. We're used to the idea of hot objects actually glowing because of how hot they are, like metal or like lava. And the sun is actually the same. The reason it glows is because it's hot. But this phenomena is called blackbody radiation. So look at this glowing bit of metal. You can see that the hot bit is glowing way more than the cool bit. But not just that, the colors are different. So the hot bit is glowing yellow, whereas the less hot bit is glowing red. If you look at the spectrum of visible light, like this one or like that one behind me, you can see that red is on top because it has the longest wavelength. And then you have purple at the bottom because it has the shortest wavelength. And what happens is the hotter an object is, the higher its color gets. So what happens is that all hot objects actually glow. Like even we glow in the infrared spectrum. But the hotter the object is, the more its peak color moves down the spectrum. We see that with the glowing metal object, where it has a more reddish tone when it's a little bit cooler, and a more yellow-like one when it's a bit hotter. But actually, even for a glowing hot piece of metal, the majority of the light that they put out is in the infrared spectrum, so like way down here. That's because even though they're very hot, they're not hot enough to mostly be glowing in this part of the spectrum. So that means that we can see them glow clearly in an infrared camera, but we can't see the majority of that glow with our own eyes. The sun, however, is very different. While the majority of hot objects on Earth are only hot enough to really glow in the infrared spectrum with a tiny bit of overlap with the visible spectrum, the sun is really hot. It's really hot, and that's why the majority of its light falls in this visible bit of the spectrum. That's the reason why the visible bit of the spectrum is visible to us. See, imagine if we had evolved to only see infrared. Well, that would be super useless to us since the sun is mostly not outputting that much infrared. It's outputting light in this part of the spectrum. And so our eyes evolved to see this bit of the spectrum where the sun is strongest. So you can see why this phenomenon of blackbody radiation is super important. Understanding why the sun glows in the way that it does is what explains why our eyes are the way that they are. And it explains why, for example, leaves are green. And so we want to understand exactly what the spectrum of the sun looks like. But around the 1900s, physicists realized that they didn't know how to explain this phenomena, and it caused quite a crisis in physics.
Imagine this is the sun, and it's radiating light outward. But there's also a bunch of light bouncing around inside it. Of course, there's a lot of molecules inside the sun, like hydrogen, that'll happily absorb a bit of that light. And after a while, they'll spit that light out again, but they might output it as a different color. The light that escapes from this process is what ultimately reaches us on Earth, and so the colors of that light are the colors of the sun to us. We know that the sun mostly outputs rainbow light, but with a bit more green than anything else. The question scientists needed to answer was, why green? Now, to try and answer that question, we're going to simplify things. We know that light in the sun is likely to be absorbed very quickly, but there are tiny gaps available in between all of these obstacles where the light can just be without being absorbed. Say on average, light can travel a distance of L in any direction before being absorbed. In the rest of this video, we're going to try and model what happens inside of this tiny pocket of freedom before the light gets absorbed at the walls of this sphere and then re-emitted. So we're going to assume that this little sphere is hollow, but it has metal walls that, easily absorb and then re-emit light. So that's the simplification that we're going to make for the rest of our analysis. And now we want to find out, what color is this sphere going to be?
So the people in the 1900s were assuming that light is a wave, and using that theory, they were able to get quite far in terms of predicting the color of objects. So this is as far as they got. So in the classical theory of light, red light has longer wavelength than, let's say, blue light, which has very short wavelength. So what that means is that red light waves around with much lower frequency than, let's say, blue, which is waving around with very, very high frequency. So that's why we call red light low frequency light and blue light high frequency light. You'll also notice that I've made the constraint that all of this light goes to zero on both ends. And that's because of this sort of box constraint. Outside of this box, the light is zero, and so on the edges, we need to constrain it to be zero. But once you add that constraint, you do something a bit weird to light. So the usual spectrum of light is continuous. There's this red light, but there's also a slightly more orange version of this red light that has a slightly different wavelength. But that wavelength won't fit into this box. It might end here rather than right here. And so it wouldn't be allowed inside of the sphere. So that means that you've picked out certain colors from the full spectrum that are allowed to be inside of the sphere. So now we only need one more rule from classical physics to end in complete disaster. So in classical physics, when there are different ways that this object can dump its energy, in this case it's going to dump its energy into any one of these colors, then classical thermodynamics tells us that it is equally likely to put its energy into every one of these different modes. Now, I've only drawn 4 of these modes, but there are actually an infinite number. You can't fit too many bigger waves in, so there's like a slightly more red that would just about fit in here. But you can fit way more violet and ultraviolet light in. So, okay, imagine this pen is purple, so violet, and I could fit in something that goes like this instead. Yeah, sorry, I definitely didn't do that right. But you get the idea, something that has twice the frequency of the blue light. So that is going to also fit in there. And then something that has 3 times the frequency and 4 times the frequency, all of those are going to be allowed. So there's an infinite number of them. So if all of them take their fair share of the energy, then instead of glowing in any of the other colors, most of the light is going to be coming from the violet and ultraviolet part of the spectrum. So that means that every single object should be blazing in the ultraviolet spectrum, which we don't see. So this was called the ultraviolet catastrophe. So I don't remember exactly what year this was. I think somewhere around 1910, Max Planck came along and he thought, why don't we try and fix this by doing something a little weird? He proposed the idea that light's energy is quantized. Okay, so here's how we're going to model what Planck did. So he said, imagine that this object has a particular temperature. Let's call it T. So the higher T is, the more energy there is to go into each of these different colors of light, all the way from red up to violet. But there's nothing special about any one of these types of light. There's no reason that, for example, red should end up with way more energy than, let's say, purple. So classically, what should happen is that all of the energy eventually kind of ends up being equally distributed. The way that this happens is that if you think about the light inside of this sphere, sometimes, let's say, the red light might have a whole lot of energy, and so that energy might get absorbed by the outer sphere, and that outer sphere might eventually re-emit that light into a different color. Maybe it will split it up between yellow and green. But if this keeps on happening, that all of these colors are constantly transferring bits of energy to the wall, which then transfers it to different colors, then you can imagine how eventually this will just sort of equilibrate and each of these colors will have the same amount of energy. But this is a problem for us because there are loads of colors in the ultraviolet spectrum which also do fit inside of this sphere and all should get an equal amount of energy. But here's Planck's solution. Right now, we're assuming that any amount of energy can be transferred. So we can take a tiny little bit of energy from here and put it over here, and that's no issue. But Planck said, what if this is impossible? What if each color of light has a minimum bar of energy that they're willing to take at any one time? And his real innovation was realizing that this sort of minimum quanta of energy that light will accept is different for different colors. So for example, red has a very low threshold. It will accept energy chunks in quite small packets. But as we go further down, the light gets a little bit more picky about how much energy it's willing to accept. So orange might have a slightly higher threshold. And as we go down, the thresholds get bigger until eventually they get kind of unreasonable. So violet light is only happy to take a huge chunk of energy at a time, whereas red is basically happy to take even very little bits of energy. So imagine what's going to happen. Every time this wall has some excess energy and it wants to radiate it out as one of these colors, if that energy doesn't meet the bar for, let's say, violet light, then it will have to radiate it out as one of the other colors. Every time that this wall has gained some energy and it wants to give it away by radiating into one of these colors, if that amount of energy is too small to, for example, be purple or to be blue, then it'll have to be radiated as one of the other colors. So for example, it might nicely split up into chunks for red. So that means that red is more likely to take that energy. It's only on the rarer occasions where this hot object has a big chunk of energy that it might be exactly what purple was looking for. And so if we let this play out for a while, what we find is that red will end up with far more energy than the other colors. And so if you let this play out for a while, you can see how violet light would end up with less than its fair share. And that's how Max Planck averted the ultraviolet catastrophe. But by this reasoning, you should expect red light to be the most dominant. But it's actually not, and the reason is a little subtle. Remember I said that only colors that are exactly the right size to fit in this object are allowed. So there's more than one color in the red part of the spectrum. So maybe this other red also fits into the object. So there are a couple of different types of red that are allowed here. When you're in a part of the spectrum, like blue, that's shorter wavelength, there are more shades of blue that are going to fit inside of this object, and each one of them deserves its equal share of energy. And so that's why, even though this reasoning skews the light towards red, this reasoning skews the light towards purple, and they end up meeting in the middle. The actual energy distribution looks more like this, and this is what Planck predicted for the sun. that the main color of light that the sun is outputting is going to be green. Yes, it outputs in all of the visible spectrum, but the peak is definitely in green. Now you might think that that doesn't actually matter for everyday life. Like, what does it matter if the peak is actually in green versus in yellow? But to our eyes, it makes a huge difference. If you've ever played with laser pointers, you might have noticed how much brighter green laser pointers seem to be. At first, I thought that was just because, people who make green laser pointers must be more irresponsible and just make them really bright. But that's not actually the main culprit. And I only noticed this when I bought a green laser and a red laser that were the exact same power. The green one looked way stronger. And that's because our eyes are super sensitive to green because the sun is outputting quite a lot of green. And so objects around us that are illuminated by sunlight tend to be a bit more green. So it makes sense for our eyes to specialize in that color. And another phenomena where the greenness of light apparently matters is in the fact that all leaves seem to be green. Why is that? In fact, that seems really weird because if green is the main energy being outputted from the sun, shouldn't leaves want to absorb that energy? Well, the problem is that there's too much green. Like, if plants actually absorbed all of that green light coming from the sun, they would probably burn. And so they prefer to, in fact, absorb light from the other bits of the spectrum and reject light that's green. So that's why they look green to us. It's because they're rejecting the green light, and so it's being reflected back into our eyes. So yeah, even though the sun looks like it's pure white, equal in all of these colors, the fact that it peaks in green actually does make a big difference for life on Earth. And all of this came from Planck's crazy idea that light is quantized into chunks, and the size of those chunks depends on frequency. Now, I don't know what Planck was thinking when he did this. I don't know if he realized what kind of revolution he had started. I think maybe he did, because he seemed to be pretty troubled by it. But it was Einstein who really took this idea from Planck and ran with it. He realized that you could use this same quantization of light to explain something called the photoelectric effect. Both he and Max Planck ended up winning the Nobel Prize for their work on the quantization of light, because genuinely this started a revolution. The idea that waves, like light, can only be absorbed and emitted in chunks like they're particles is what started the quantum revolution. And all of that came from figuring out why the sun is mostly green.